Hello, in this lesson we'll continue our discussion of our natural deduction system. We've already covered what we could call the basic or fundamental rules of our system. These are introduction-elimination pairs for each of our 5 connectives, for a total of 10 rules. These rules are complete, in the sense that for every valid argument in a cell, there is a corresponding derivation using just these rules. So they are enough for showing validity in a cell. However, in the course of doing derivations, it is often useful to supplement our basic set with an additional package of derived rules. Strictly speaking, these new rules really don't do anything that can't already be done with our basic set, since every use of a derived rule can be replaced by a combination of applications of primitive rules. So, in a sense, they don't bring anything new to the table. But if so, then why would we want them? The answer is for convenience. These rules are shortcuts that make our derivations shorter. For instance, this is a derivation of the argument whose premises are in the first 2 lines and whose conclusion is in the last line. Here, I'm just using the basic 10 rules, and it took me 23 steps. But if we incorporate a couple of derived rules, which we'll study in a couple of minutes, we can bring down the number of steps to 12. So the derivation is now almost half as short as it was before, and is much less complex in the sense of requiring fewer subderivations. Now, if these rules are so handy, then why don't we incorporate them into our official system, instead of treating them as mere accessories? Well, like so many things in life, there's a trade-off here. If we're using the system to prove things about specific sentences or arguments by doing derivations, then it is convenient to have many rules. And this is what we'll be doing in this course, to be sure. But if our object of study is no longer this or that sentence, or this or that argument, but the logical system SL itself, then it is better to have fewer rules because it makes the system more compact, and proofs about the system are clearer and more economical. So it pays off not to add too many rules to the system. This advantage, well, is only evident in more advanced courses in logic. So to keep things even between the needs of the beginner and the needs of the intermediate student, we'll take our 10 elimination and introduction rules as the official core of the system, and everything else as bells and whistles. But how do we go about adding a derived rule to our inventory? A derived rule is introduced with the aid of a proof, which shows how any of its uses can be replaced by applications of primitive rules. What makes the use of a derived rule legitimate is that anytime we apply them, we can in principle replace them with a longer sequence that only involves the basic rules that we already trust. The first one is argument by cases, which is also known as constructive dilemma. And its form is if you have x or y, and if you have if x then z, and if you have if y then z, then you can infer z. You can visualize it like this. You can only take 2 paths, namely x or y, which I'm picturing here as a couple of tubes, or as entrances to a couple of tubes. Now, if you go down x, you end up in z. And if you go down y, you also end up in z. So, no matter which path you take, you're bound to end up in z. Here's an English language illustration of this pattern of reasoning, in keeping with last week's theme. This is the argument. I'll go to the Amazon or I'll go to Canada. Those are my only 2 options. If I go to the Amazon, I'll get sick. If I go to Canada, I'll get sick. Therefore, I'll get sick. There's no escaping my fate. Okay, now let's change the theme because I don't want to get in trouble with the Canadian Board of Tourism. Let's apply the rule to this SL argument. The premise is if A then C, and if B then C. Therefore, if A or B, then C. So we begin by listing our premise, and then on the right, we list the intended conclusion, which is there to indicate our goal. Now, since our goal is conditional in form, we start with the antecedent, which is A or B. So we open our subderivation with A or B as an assumption. So the subgoal, that is the goal of the subderivation, is going to be C. So we apply reiteration, the rule that we use to build character, and because our subderivations have to be self-contained, and we bring premise 1 to line 3 inside of subderivation. Then we break it down with ampersand elimination, and we get those 2 conditionals. But notice now that we have all the elements, we can derive C by argument by cases. And if you can't visualize it, then here we have the three premises. We have A or B, which indicates the two options. And then we have that if A, you end up in C. And then if you have a B, then you end up in C. And again, notice how we actually have a perfect match for the form. And from lines 2, 4, and 5, we can derive C by argument by cases. But notice then that we already achieved our sub-goal, which was C. So we can close our subderivation, and we started with the assumption that A or B, ended up with C. So we reach our conditional. A if A or B, then C, by horseshoe introduction, lines 2 through 6. Denying the consequent. This is a very useful rule. It's also known as modus tollens. It comes in 4 different forms in order to accommodate the different places in which negation could occur. The first form is very clear. It says that if you have a conditional and we deny the consequent, hence the rule's name, then we are entitled to deny the antecedent. So you had, if the cat got catnip, then it acts silly. The cat is not acting silly, therefore the cat didn't get catnip. The second form says that if X then not Y, and Y then not X. An example of this in English would be, if the cat got catnip, then it's not acting sensibly. The cat is acting sensibly, therefore the cat didn't get catnip. And don't worry about the use of the tense here, it's just for purposes of illustration. So you have if not X, then Y, and not Y, then X. This is the third form. In English, if the cat didn't get catnip, then it's acting sensibly. The cat is not acting sensibly, therefore the cat got catnip. Last, if not X, then not Y, Y, therefore X. If the cat didn't get catnip, then it won't act silly. The cat is acting silly, therefore the cat got catnip. Now, attention, you have to pay attention here. Don't confuse this valid rule, which is called denying the consequent, which we just saw, with this fallacy, which is called denying the antecedent. It says if X then Y, and not X then not Y. So if you want an example of this, look at if the cat got catnip, then it's acting silly. The cat did not get catnip, therefore the cat is not acting silly. Well, you can see that it's quite possible for the premises to be true and the conclusion to be false in this argument. So you can grant that if the cat got catnip, then it's acting silly. And you can grant that the cat did not get catnip. But you don't have to accept that it's not acting silly. It may well be acting silly for some other reason. Maybe it got drunk, or maybe it saw a squirrel in the window. I mean, who knows what goes on in a cat's mind. So this is an invalid pair of argument, and this is the fallacy of denying the antecedent. Okay, now let's proceed to the derivation of the first form. Remember that the first form is if X then Y, and not Y, therefore not X. Okay, so we list the premises, if X then Y, and not Y, and we know that we have to reach not X. And so we are going to make an assumption. We're going to introduce not X by negation introduction. And so we're going to assume X, and then our sub-goal is going to be to reach a contradiction. But actually, let me go back here. The derivation rules, just to note briefly, are supposed to apply to SL sentences. And these are not SL sentences, but meta variables. So imagine that we can substitute X and Y's by any sentence letter whatsoever, okay? Okay, so we start with an assumption of X, and then we have to get the contradiction Y, not Y. And then we apply reiteration to get our first premise, and then by horseshoe exploitation or horseshoe elimination, we get Y. Now we bring down not Y from 2 in order to have the contradiction nested inside our subderivation. So notice that we reached our sub-goal, so we close the subderivation, and we get not X by negation introduction, lines 3 through 6. So we have proved our derive rule. Now let's do an application to a particular argument. So let's show that this argument is valid. So the conclusion is not E. So we cite our premises, and then here to the right, we have a reminder that our conclusion is not E. Now, not E occurs here as a consequent of this conditional. So it looks like one way of getting this would be to get not D. So let's keep that in mind. We have to get not D. And one way to get started is, notice that it's basically conditionals that can be broken by themselves. But you have here that in sentence 1, C is the consequent. And on 4, we have the negation of that consequent. So we can apply the rule of denying the consequent to get not A or B. Lines 1, 4. And again, we have the same situation. In 2, we have the conditional, and on 5, we have the negation of the consequent of that conditional. So this is another situation from denying the consequent, and we get the negation of the antecedent, that is not D. And not D is what we're looking for. So we can apply horseshoe elimination in lines 3 and 6 to get not E, and we have reached our goal. Now for a digression. We already have the 3 dot symbol, which means therefore, more or less. Now, to simplify the statements of some of our following derived rules, I'm going to introduce another symbol in our meta language. This is the 4 dots, and it means approximately is equivalent to or is interderivable with. I have to be a bit vague at this point. So here's the convention for reading the 4 dot symbol in what follows. Read x 4 dots y as a combination of infer y from x and infer x from y. So this gives rise to 2 kinds of rules, depending on which symbol we use to express dependencies among the relevant sentences. Implicational rules, or 3 dot rules, are strictly unidirectional. They only work left to right. They say that y is inferable from x, and don't say anything about whether x is also inferable from y. Equivalence rules, on the other hand, also known as 4 dot rules, are two-way. They work left to right and right to left. Moreover, implicational rules apply to whole sentences only, whereas equivalence rules can also apply to parts of sentences. To see why, go back to our previous discussion of the substitution of equivalence, since the set of 4 dot rules is exactly the set of equivalence laws we introduced earlier. Conditional elimination is an example of a 3 dot rule. It's illegal to detach the consequent of a conditional that is part of a larger sentence, as in this illustration. To apply conditional elimination, we would first have to pry if A then B apart from C, so that it stands on its own in a separate line. De Morgans, on the other hand, can be perfectly applied to the antecedent of a conditional. Okay, this is the end of the digression. The next rule is contraposition. This rule describes what happens when you swap antecedents and consequents in a conditional, an event that always involves introducing or eliminating negation signs. And we're going to include these 3 forms into our list. Now we have the conditional, and this just cites the equivalences that we're already familiar with, namely that if x then y is equivalent to not x or y, and the negation of a conditional is equivalent to x and not y. Then we have weakening, which is y, therefore if x then y. This may look odd at first glance. Where did the x come from? You can make sense of it by remembering that whenever the consequent of a conditional is true, the whole conditional is true, independently of the antecedent. So given that y is true in this case, it doesn't matter which sentence x you use as antecedent. The sentence if x then y will be true. This is completely analogous to the disjunction introduction rule, and here you can see another instance of the parallels between disjunction and the conditional. Then we have our old friend De Morgans, in the form for disjunction and the form for conjunction. Okay, let's do some exercises that apply the last rules that we introduced. Let's show that this argument is valid. Okay, these are the premises, and then we have the conclusion in the corner, and we see that it's conditional in form. So we're going to use horseshoe introduction, and we open a subderivation, and the subderivation is going to contain as assumption the antecedent of the conditional that we want to introduce, which is not B or C. And then what we want to reach in this subderivation is the consequent, D and not A. So the goal of this subderivation or subgoal is going to be D and not A. And the only way to reach that is to get D and not A separately and then join them with ampersand introduction. So we have these two other sub-goals, D and then not A. Okay, so we apply De Morgan's on 3, you get not B and not C, and then we detach these two conjuncts. And then we have them separately in lines 5 and 6. Now, I apply denying the consequent on lines 1 and 5 to get not A. Now, did you notice what I did here? Or rather, what I did not do? I exploded a sentence from the outer derivation without using the reiteration rule. So yes, from next week on, you can skip the R rule. And so you're freed from the heavy burden of having to rewrite sentences in your subderivations. But wait, I'll let you skip the rewriting as long as you remember to do the step in your mind. Promise? Okay, let's go on. So we already had not A, so that's one of our sub-goals. And we cross it out. And notice that we can get D or A also, right? Because we have the conditional if not D or A, then C, and then we have not C, so we can get D or A. Lines 2, 6, denying the consequent. And then finally, we can get D from not A and D or A by disjunction elimination. So we get we have all our sub-goals. We have D and not A. We can join them together from lines 7 and 9. And we can close our subderivation. We have our whole conditional. Okay, let's do another exercise. Again, our conclusion is a conditional. And since this is a conditional, we're going to start with an assumption, a subderivation, and the assumption is going to be A. And again, our sub-goal is going to be a conjunction, E and not D. And in order to reach that sub-goal, we have to get E, and we also have to get not D. So we can apply De Morgan's in 1 to get not A or not B or C. We get not A or not B or C by De Morgan's from 1. And our next move is to get not B or C by V elimination from lines 4 and 5. But, well, this doesn't really fit with the V elimination rule as stated so far, which I'm repeating here in these two versions just for reference. If you look closely at the prescribed form, the second premise is always negative, whereas the conclusion is not. So to follow the rule, in all strictness, I would first have to get not A from A, and then combine that with line 5 to get not B or C. But I'm skipping this step, and I will be invoking an enhanced version of the rule that incorporates double negation. We can call it V elimination plus, and it goes like this: not X or Y, X therefore Y. This is the version I'm invoking on line 6. Okay, so we can apply De Morgan's to get not B and not C, and then we detach the conjuncts, and we're in a position to get not D by denying the consequent lines 2 and 8. So I have one of our two letters that I have to get separately. And then I'm in a position to get E by V elimination lines 3 and 9. So I can build E and not D. I join them with ampersand introduction, lines 10 and 11. So I have reached the consequent of the conditional I wanted to introduce. So I close the derivation and I write my conclusion. It's by horseshoe introduction, lines 4 through 12. Now let's do a couple more rules. Another rule which we could introduce is double negation, which says that if you have X, then you can introduce not X. And then reductio ad absurdum. Last week, we mentioned an informal example of this, but now we can incorporate it formally into our system. So it's also known as indirect proof, and we can use it to derive non-negative sentences by using the same procedure as negation introduction. So basically, if you want to derive A, you assume not A and derive a contradiction. But if you only have negation introduction, then, well, this would yield not A as a conclusion, right? Because this rule can only introduce tildes at the end. What you would do then is, by negation elimination, you would get A. Now, reductio ad absurdum allows us to skip the last step. That is, you assume not A and derive a contradiction from which you can directly conclude A. So we save basically one step. And here's the rule in graphical form. You start with a negated assumption, not X. And then you arrive at a contradiction. Finally, once you reach your contradiction, you can conclude X by reductio ad absurdum, and then you cite the lines that comprise the subderivation. Let's apply this to this argument. This argument is similar to an example that we just gave, but there's a slight difference. So suppose that we have to prove E by RD. Then what we do is that, well, list the premises, and then we start not E, that is the negation of what we want to prove. That's the assumption for RD. Okay, and our goal, of course, is to get any contradiction. So we apply denying the consequence to get D, and we can detach the consequence from lines 2 and 6, and finally we can get C by horseshoe elimination, lines 1 and 7. And notice that we also have not C, and I'm going to bring it down here so you can appreciate the contradiction here. I'm going to bring it down so that the contradiction is entirely within the subderivation. But you don't have to do that. Since I am allowing you to skip reiteration, I'm going to do this consistently. But the point is that we have a contradiction, so we can close our subderivation, and we conclude E by reductio, lines 5 through 9. This is all for today. Bye.